Section 1, Introduction. Surveying and geomatics play a crucial role in our understanding of the world around us. These fields involve the measurement, analysis, and representation of the Earth's surface and its features. Surveying has been an essential practice for centuries, enabling us to map terrain, design infrastructure, and manage land resources. Geomatics, a more recent term, encompasses surveying and extends its scope to include the use of advanced technologies such as GPS, remote sensing and geographic information systems, or GIS. The importance of surveying and geomatics is evident in various aspects of our lives. From the construction of buildings and roads to the management of natural resources, accurate spatial data is essential. Surveyors play a crucial role in determining property boundaries, creating maps for navigation, and monitoring environmental changes. In an increasingly complex and interconnected world, the ability to accurately measure and represent the Earth's surface is more critical than ever. Surveying and geomatics rely on a combination of traditional tools and cutting-edge technology. Section 2, Traditional Surveying Instruments. Total stations are sophisticated instruments that combine electronic distance measurement, or EDM, with electronic angle measurement. They allow surveyors to determine both the horizontal and vertical position of a point with high accuracy. A total station emits an infrared laser beam to measure the distance to a prism reflector. By measuring the time it takes for the beam to return, the instrument calculates the distance. The angle measurement is achieved through electronic encoders that track the rotation of the instrument's telescope. Levels are used to determine elevations and differences in elevation between points. A level consists of a telescope with a crosshair that is precisely aligned with the direction of gravity. By sighting through the telescope and reading the elevation on a graduated rod held at the point of interest, surveyors can determine the elevation of that point. Levels are essential for tasks such as setting out building foundations, constructing roads with consistent slopes, and measuring the volume of earthwork. GPS receivers have revolutionized surveying by providing a highly accurate and efficient method for determining positions. GPS relies on a network of satellites orbiting the Earth that transmit signals containing their precise location and time. A GPS receiver on the ground receives signals from multiple satellites and uses triangulation to calculate its own position. By combining measurements from multiple satellites, GPS receivers can achieve centimeter-level accuracy, making them invaluable for a wide range of surveying applications. Section 3, Surveying Techniques. Traversing is a fundamental surveying technique used to establish a series of connected points known as traverse stations over a large area. The process involves measuring the distance and angle between each pair of consecutive stations. By starting from a known point and progressively measuring distances and angles, surveyors can create a network of points that can be used to map the terrain or establish control for other surveys. Traversing is commonly used in land surveying, road construction, and large-scale mapping projects. Leveling is the process of determining the elevation of points relative to a known datum, usually mean sea level. Differential leveling, the most common method, involves setting up a level at a known elevation and taking readings on a graduated rod held at the points of interest. By comparing the readings, surveyors can determine the difference in elevation between the points. Leveling is crucial for tasks such as setting out building foundations, constructing roads with consistent slopes, and monitoring changes in elevation over time. Triangulation is a technique used to determine the position of a point by measuring the angles to it from two or more known points. By forming a triangle with the point of interest and the two known points, surveyors can use trigonometric principles to calculate the distance and position of the unknown point. Triangulation has been used for centuries in surveying and navigation, and it remains a valuable method for establishing control points and creating accurate maps. Section 4, Geographic Information Systems, or GIS, have emerged as powerful tools for managing, analyzing, and visualizing spatial data. GIS software integrates data from various sources, including surveys, satellite imagery, and aerial photography, to create interactive maps and conduct spatial analysis. This enables users to visualize data in different ways: query the data to extract specific information, and perform complex spatial operations to gain insights and make informed decisions. Surveying data forms a crucial foundation for GIS applications. Accurate measurements of distances, angles, elevations, and positions provide the basis for creating precise maps and spatial databases. GPS data, in particular, has become increasingly integrated with GIS, providing real-time location information for a wide range of applications. The integration of surveying and GIS technology has enhanced the capabilities of both fields, enabling more comprehensive and efficient spatial analysis. GIS has found applications in numerous industries, transforming the way we understand and interact with the world around us. In urban planning, GIS is used to analyze land use patterns, optimize transportation networks, and manage infrastructure. In environmental management, GIS helps monitor deforestation, track wildlife populations, and assess the impacts of climate change. In agriculture, GIS is used to analyze soil conditions, optimize crop yields, and manage irrigation systems. The versatility of GIS has made it an indispensable tool for decision-making in various fields. Section 5. GIS applications. In urban planning, GIS is used to create detailed maps of cities, showing the location of buildings, roads, utilities, and other infrastructure. This data enables planners to analyze land use patterns, identify areas for development, and optimize transportation networks. GIS can also be used to model the impact of proposed developments, such as new roads or buildings, on traffic flow, air quality, and other environmental factors. By providing a comprehensive view of the urban environment, GIS helps planners make informed decisions that promote sustainable and efficient city development. In environmental management, GIS plays a crucial role in monitoring and protecting natural resources. GIS can be used to track deforestation rates, analyze the health of forests, and assess the impacts of climate change on ecosystems. By integrating data from satellite imagery, aerial photography, and field surveys, GIS provides a powerful tool for understanding environmental changes and developing effective conservation strategies. GIS is also used to manage wildlife populations, track the movement of endangered species, and identify areas for habitat restoration. In agriculture, GIS is used to optimize crop yields, manage irrigation systems, and analyze soil conditions. By creating maps that show the spatial distribution of soil types, nutrient levels, and other factors, farmers can tailor their planting and fertilization strategies to specific areas of their fields. GIS can also be used to monitor crop health, detect pests and diseases, and manage irrigation systems more efficiently. The use of GIS in agriculture has led to increased productivity, reduced environmental impact, and improved food security. Section 6. Conclusion. Surveying and GIS technology have transformed the way we understand and interact with the world around us. From traditional surveying instruments to sophisticated GIS software, these tools have enabled us to measure, analyze, and represent the Earth's surface with unprecedented accuracy and detail. The applications of surveying and GIS are vast and continue to expand, impacting various aspects of our lives. In professional contexts, surveying and GIS are essential for infrastructure development, land management, environmental monitoring, and resource exploration. These technologies provide the foundation for accurate maps, spatial databases, and decision-making tools that drive efficiency and sustainability in various industries. The integration of surveying and GIS has created new possibilities for understanding complex spatial relationships and addressing challenges related to urbanization, climate change, and resource management. In everyday life, surveying and GIS technology are increasingly integrated into our daily experiences. GPS navigation systems rely on surveying data to guide us to our destinations, while online mapping services utilize GIS to provide us with information about our surroundings. The use of GIS in urban planning, environmental management, and agriculture has indirect but significant impacts on our quality of life, influencing the design of our cities, the conservation of natural resources, and the production of our food. As surveying and GIS technology continue to advance, we can expect even more innovative applications that will shape the way we live, work, and interact with the world.